6.3 for the third time, right? Okay, we're going to finish up 6.3 today. Last time we had just gotten to the point where we were looking at theorems of exponents. So let me pull that slide back up where we were. And we had written these theorems down. And the next thing we're going to do is we're going to explain why they work. There's a couple, at least one for sure, but I think there's a couple that are actually like proofs, like real proofs. They keep things really generalized. The others, I'm just doing a case example so you can see why it works, which is enough for what we're working with, I think, to see how that's happening for us. So the first one, the rule that we had, the property says that we're going to add the exponents. And to justify that, we're going to look at the example of what happens when we have a to the third times a to the fourth. So a to the third means, by definition, it's 3a's multiplied. And a to the fourth means I have 4a's multiplied. So all I've done is I've broken down what the exponent definition is for these two terms. And if I have a to the third and a to the fourth, I have 3a's and then I have 4a's. How many a's is that? 7a's. So there are 7 of these. So again, by definition, this means I have a to the 7th. And if you take a look at the exponents, 3, 4, and 7, how do you get 7 from 3 and 4? You add them, okay? So this shows a really good justification with small enough numbers that you can do it with a child to explain why it is that we're adding as opposed to, say, multiplying, which might be an inclination to try instead. The next one is subtraction. So again, it's not exactly proof by example, but at least justification by example. We're going to do a to the 5th over a squared. So a to the 5th means 5a's, again, by definition, over 2a's. And then one of our properties that we've encountered back in 6.1, I think it might have been 6.2, was the ability to reduce fractions, right? The fundamental principle of fractions. And so we have the ability to cancel one from the top because they're all multiplied. It doesn't work with addition, doesn't work with subtraction, it works with multiplication only. So because they're all multiplied, we can cancel them term on the top and the bottom, leaving me with 3a's. And that's otherwise known as 3. So an exponent a cubed. And how do I get from 5 and 2 to 3? I subtract. You do need to be a little bit careful when you're trying to show these that you avoid things that might actually work to make it look like multiplication. For example, on this first one, if I had decided to do a to the 2 times a to the 2, well, 2 plus 2 is 4 and 2 times 2 is 4, so it wouldn't really show what I was trying to show. So there are some examples that are not helpful to try and use. Typically, if you stick with 3s and 4s and 5s and stuff like that, you kind of avoid all of that. All right, the next one we said was multiplication. So a to the m times to the n is a to the mn, and we multiply the m and the n together. Are my m and n running together enough that I should shift it? I'll do that. And again, some justification for that. So let's use a to the third and then squared. So a to the third means that I have 3a's. And then squaring the a to the third means I have 3a's twice. But how many a's is that? 6. And how do you get from 3 and 2 to 6? You multiply. Okay. Number 4 actually has the exponent sort of distributing or applying to each of the individual pieces. Again, it only works for multiplication and in a moment division. This doesn't work if it's a and the b are added or a and the b are subtracted. Okay, it's just because they're multiplied and soon to be divided. But this says that I would distribute. I have a to the m and b to the m. And for this one, we'll do ab cubed. So ab cubed, by definition of exponents, means I have ab 3 times. And then I'm going to shuffle the letters around. I want to move them. I want to group the a's at the beginning and the b's at the end. You can't just do that. The reason you can do that, though, is because we have two properties that allow that. the commutative property that says you can alternate two numbers, right? 5 times 3 is 3 times 5. And the associative property, which says you can regroup things in different groupings. So using those two properties, I am able to regroup these three to have the a's together and then have the b's together so that I have a cubed, b cubed. And so you can see the 3 coming through to each of the a and the b terms. Number 5 works almost identically in terms of showing it. So I have a distribution again, a to the m over b to the m. And for an example, we'll still use cubed. So we have a over b cubed. And so I have a over b times a over b times a over b. It's easier because there's no commutative and associative I even have to apply here. I simply use the property of fractions for multiplication, right? Like the definition, I just multiply across the top, multiply across the bottom. So I have 3 a's, I have 3 b's, or shorthand a cubed over b cubed. Now let me reiterate something that I'm pretty sure I said last time, but maybe I didn't, just to make sure it's been said. I'm not expecting you to show this to me. This is for your benefit only, because some kid's going to ask you some point if you're teaching anything like this. But why? And you'll be like, oh, I remember we talked about that, and you'll be able to go and either search for it or grab it notes or something like that. Or maybe you'll be able to reason enough through it and say, I need to show them an example, and you can create an example. The other thing is that even on your homework and so forth now, we're using the properties and rules. We're not trying to recreate them every time. So if you have a property that says to find out, how to simplify something, which we're going to do in a moment, we're not trying to recreate the wheel, which is kind of what we're doing right now. We're just going to use the properties as is, okay? So the sixth one is a negative exponent. And so negative exponents flip fractions. It's a reciprocal notation. So the fraction flips upside down, b over a. I'll do an in-between step. That's what makes the exponent positive. And then it becomes the same as property number 5 above it, and I distribute the m, so b to the m over a to the m. And we'll do the same thing we did on the last one, but do a negative 3 exponent instead of a positive 3. So I'll do it in a different order just so that you can see that it doesn't matter. A to the b is cubed, and then we're going to raise it to the power negative 1. So we're kind of using property number 3 in reverse. We're separating negative 3 into two pieces, 3 times negative 1. The power of 3 means that I have a cubed over b cubed. And then the exponent negative 1 tells me to flip it. So I have b to the negative 3. B to the 3 over a to the 3 to flip it. Okay, that negative exponent means reciprocal, or it means multiplicative inverse. Okay, there's 2 more additional properties that we're going to throw in here. One of them I'm going to show you in a true legit proof. So it's a to the 0. Do you remember what a to the 0 equals? We have not written this down yet. 0. Nope.
1.
It's 1, yeah. A to the 0 is 1. Do you remember what happens when you have a to the negative n? It's kind of like property 6. So on property 6, we took the a over the b and then we flipped it. Right now, we have the equivalent of having an a numerator and a 1 in the denominator. So when we flip it, it actually gives me 1 over a to the n, or we can write that as 1 over a to the n. I don't need to worry about distributing the n to the power 1 to the value 1 on top, because 1 to the n is just 1. Okay. 7 is very clever, so I want you to take a look at this one. I think it takes a lot of faith to just say a to the 0 is 1, and that's probably why it's hard for us to remember, because it sort of has no bearing as to why. So take a look at this. If I have a to the 0, I'm going to write 0 slightly differently. I'm going to write it as n minus n. That's 0, right? It is. And then I'm going to use property number 2 in reverse. So property number 2 over here starts out saying I have a to the m over a to the n, and I subtract it. I'm going to start with the subtraction because I've got a to the n minus n, and I'm going to move it back into a division statement. So this creates a to the n over a to the n like this. What happens when you divide a number by itself? It's 1. So this a to the n over a to the n is exactly the same on the top and the bottom. Therefore, it equals 1. And if you didn't want to do it generalized like this, could you make the n a 3 for a child? Sure. I mean, there's nothing wrong with making it more specific, a single case. All right, our last one, justification by example. We're going to do a to the negative 3. Okay, so we talked about the fact that the negative makes things a reciprocal. The reciprocal of 1 over a, the reciprocal of a is 1 over a. And then we'll do the power 3. So the power 3 cubes the top and cubes the bottom. But as you mentioned before, when we cube the top, because it's a 1, we just get 1. So you can see that negative 3 showing up as a power of 3, but only in the denominator on this one. So what we're wanting to do now is we're wanting to take all these properties and we're wanting to utilize them to simplify expressions. Shift some values around, consolidate some things, stuff like that. So our directions say to write in simplest form with positive exponents. So no negative exponents when we're done. Simplest form means that I don't have repeated bases, right? So like right now this part, number A, letter A, is not in simplest form because there's an A on top and an A on bottom, right? That's what makes it not simplest form. There's lots of ways to do these problems. You can apply the different properties. There's 8 of them in different orders. And so there's lots of different looking solutions for this particular problem. One option is you could just use that second property where you subtract. Look, I've got an A on top, I've got an A on bottom. This A on top is a 1, the A on bottom is a negative 3. I can do 1 minus negative 3. Okay, so I'm going to do that first, and then I'm going to show you an alternate way. There's others besides these two, but at least to give you some thinking of different options. So if I think of it like that, this is 1 minus, and it's negative 3 in the denominator, so keep that in mind. It's the exponent in the numerator minus the exponent in the denominator. If it's a negative, it stays negative, so I have minus a negative. The B is 4 minus 2. So what happens when I have 1 minus negative 3? Like that. So I end up getting a to what power? The 4. How about 4 minus 2? 2. So on this one, not all problems like this work out so well in one step. It was a one-step problem by using this method. Let me show you another option of how you can think about this. Instead of actually using that property where we subtracted, I'm going to use a property that says that, it's the last one we just did, that says that if it has a negative exponent, it can be shifted to become a positive exponent. And the interesting thing about negative exponents is that they can shift from the numerator to the denominator or denominator to numerator and change. So on this one, I've actually got something in the denominator, the a cubed. So I still have the a on the top, I still have the b to the 4th on top, and I still have the b squared on bottom. None of that changed because all those exponents were already positive. But I can move the a to the 3rd up and make it positive. And then I can either use a property where I add exponents or I can simply count. I have 1a and 3 more a's. That's 4 a's, right? On the bottom, on the top I have 4 b's, right? And I have 2 b's, so 2 of them cancel out. That leaves me with b squared. There's really not one way to do these things, and there's not one that's better than the other. Sometimes one will work better in a certain situation than the others, but no in general kind of things are going to happen with that. So take your pick. B is a little bit different. First of all, B doesn't have any variables in it. And actually that makes it harder. Having variables makes it easier because it's easier to identify what matches. On these, it looks like 2 to the 5th, 2 fifths and 4 25ths just don't match. The problem is that they can be altered and changed so that they do. And that's harder to see with numbers than it is with variables. So if you think about the number 4, how can you break 4 down to look like a 2? 2 times 2. So I'm just going to put this down here for a second. looks terrible, but we'll go with it. How about 25? How can you break it down so it looks like fives? 5 times 5. And in doing so, we can recognize that this is 2 over 5 squared. Because we have 2 being squared on the top and 5 being squared on the bottom. We didn't have to do that with variables. Might be the only time you've said recently, I really like variables better than numbers. They really are easier for this. So, as we're taking a look then up here, the 2/5 to the third stays. This whole piece over here that has the power of -6 is going to stay as well. I'm going to leave it like that. But inside of this, I have a 2/5 squared. Lots of parentheses going on. All right, so what is something you see that we could do now? Which exponents, Lauren?
The -62.
Yep, these two exponents can be multiplied. That's property number 3. Okay, so I can rewrite the 2/5 at the beginning that has the power of 3. And then now I have a 2/5 to the power of -12. It may be tempting to deal with the fact that I've got a negative. I mean, I gave you that as an option before, right in the last problem. It's not real helpful here to do that. In order to combine these, the bases need to be the same, and they are right now. Take advantage of that fact. They both say 2/5. So what can I do next?
Add the exponents.
Mm-hmm. This is property number 1. I can add the exponents. So what is 3 and -12 added? -9. Okay, we're really close to done. I mean, we have simplified a lot to this point. Looks way better than it started. What part of the directions have we not satisfied, though? Yeah, the positive exponents part. So how do we change this so that it will have positive exponents? Flip it. Yeah, we flip it or we do the reciprocal. So we're going to do 5/2 now to the 9th. And you can leave it like that, or you can write it as 5 to the 9 over 2 to the 9. Neither one is more correct than the other. Either one works just fine. All right, we good? Doing good so far? Okay. One of the things that exponents allows us to do is to solve some different kinds of equations that we couldn't solve before. And in particular, these are exponential type equations. And the ones we're going to be looking at specifically are ones that have the same base properties. So you see on this example A base of 2 showing up multiple times. So we're going to be using exponential properties, and then we're going to be making some additions to that after we do so. So when we're taking a look at the left-hand side for starters, because they have the same base, what can I do with those exponents? Add them. So on the left, this becomes 2 to the n plus 7. Okay? Now, I don't like the 64 on the other side. Not written that way anyway, because I can't do anything with it. Much like what's on the left, I wanted them to have the same base, and they do. I need the same base on the other side as well. So how can I change 64 to be a base of 2? So you might not know. You could play with it to try. You could also just do some division steps. So what is 64 divided by 2? 32. Divided by 2 is? We're just going to keep going. Divided by 2? By 2? By 2? Okay. And we ended with the prime number 2. How many 2's are there? 6. Okay. Why does it matter? Well, because if they both say base 2 and they're equal, then their exponents must be equal as well, right? The two sides of this equation are equal, and both of them have a base of 2, so their exponents must be the same. So that n plus 7 must equal 6, So what does n have to be? -1. And if you can just see it here and you just want to write n equal -1, that's fine. If you really want to write the -7, like the subtraction of the 7, you can do that as well. Let me shrink this a little bit. Either way, you get n is equal to -1. So the goal is getting the bases to match. Now B may look a little trickier because you got a fraction on one side. But the fraction has a denominator, 81, that's not altogether unfriendly. It's a number you're familiar with. You're familiar with it because it's what? What does it break down into? What does 81 break down to? 9 times 9. So it's a number you're familiar with because it's 9 times 9, kind of like 64 is a number we're familiar with because it's 8 times 8. Right? We know we can break it down, even if we aren't breaking it down the way I'm suggesting. We know we can break it down. If you wanted to, and you don't want to keep using the first method I did, you can also break it down in a factor tree, right? Like this. So 9 and 9. And then the 9s break down into what? 3 and 3. So how many 3s are there? There are 4. Unfortunately, they're not exactly where I want them to be. They are in the denominator. How can we fix that? Yeah. But if we flip it, what has to change? You have to make it negative. And it being the negative itself, it being the exponent has to be made negative. So we change it to be in the numerator, or to pull it up, and so it's 3 to the -4, since we moved it from the denominator to the numerator. Now, this is an inequality. It doesn't say equals, but that's okay. It doesn't operate any differently, all right? So since we have the bases the same, right, the 3's match now, we concern ourselves with only the exponents, and the symbol stays the same between. So I have n is less than or equal to -4. And all the problems that you have will have the ability for the bases to do this. Does that mean all problems have this ability? Well, no, they don't. There are other techniques when problems don't fit into this sort of category, but this is a really good technique when it does. All right, next one, approximation. So we're going to approximate 20 and 1/3 divided by 9 and 7/8. So the goal is not to do the division, it's to approximate, which means to change the numbers that we are given to make it easier to work with. 20 and 1/3 is really close to what? Don't overthink this. 20, thank you. 20. And 9 and 7/8 is really close to what? 10. So this is an approximation. So this question is approximately the same as asking what is 20 divided by 10, which is 2. So why does this show up in here? Because as you're working with students on content like this, they make mistakes. And if they know that their answer, even just by looking at this without writing what I did down, should be around 2, and they get an answer that's something like 200, right? They should be like, ooh, what'd I do? It should stop making sense because the answer should be around 2. There's an expectation of what my answer should look like, and it doesn't match up. So I need to go back and figure out why. So approximating for the purposes of checking our work is useful. It's also useful for the purposes of thinking about, like I don't have a good context problem here. So this is going to sound terrible, but imagine I needed 20 and 1/3, or had 20 and 1/3 cookies, and I had 9 and 7/8 people to eat them. I know I can't have 7/8 people, but just pretend with me like we could use it for other context, right? I mean, I really don't need to know an exact answer sometimes. Sometimes an approximation is enough to answer the questions that I'm really proposing in real life. So sometimes approximating is actually much more useful of a skill than finding exact values. So it's good to practice that too. Okay, I have 2 questions that are kind of from section C in your book, or like those. Jasmine is reading a book. She has 1/4 of the book left and has read 246 pages. How many pages does she have left? So how could this sort of make sense? Well, she probably has some sort of an e-reader that tells her she's 25% done, right, or something of that nature. And she probably has a paper copy too, and maybe she's reading in a certain location, like she can't take the paper copy into her classroom, like I didn't say that right. She can't take the electronic copy into her classroom, so she has a paper copy there.
but when she's at the doctor's office, she's reading on her e-reader. Those kinds of things happen. So you have these two different sort of measures of how far she is that we're trying to sort of reconcile. So this one actually says she has 1/4 of the book left. It's really important to recognize is this is how much she has left, and the other one is how much she has read. Those are not answering the same piece of information. They're not quite the same thing, right? If she has 1/4 of the book left, how much has she read?
3/4.
So she's read 3/4. That's important. So one way to think about this particular problem, this isn't the only way, and we'll encounter in 6.4 another way to do this, is that she's read 3/4 of the book. So if X is the number of pages, we'll say total number of pages, then 3/4 times X would be the 246. Right? There's another way to do this problem. 6.4 will encounter it. But this is an equations kind of standpoint of how to think about it. How can I solve the equation 3/4 of X? 3/4 times X equals 246.
Get X by itself.
But how? Like, what would you do?
Multiply 4 over 3.
Okay, so we would multiply by the reciprocal. Cassie, are you okay? You're looking confused. What part did I lose you at?
I don't, if X is the total number of pages,
Mm-hmm.
and you're multiplying it by what she's read, that's why I'm confused.
Right, so I'm not multiplying by what she's read. She's read 246. I'm multiplying it by the 3/4 of the amount that she's read. Let's use an easy number. Let's say that there were 100 pages. So if there were 100 pages and I multiplied 100 by 3/4, I'd get 75. So if you multiply the percentage, or in this case, we're not looking at percents, we're looking at fractions. So if you multiply the fraction that she's read by the total number of pages, you'll find out the total number she's read as opposed to the total number in the book. So right now, we don't know the number in the book at all. We only know how many pages she's read. All right, so we're going to multiply by the reciprocal. I think I just wrote it wrong as I was answering the question. I apologize. Let me get that written right. 4/3 is what I meant to write. Here we go. So on the left, of course, the whole point of multiplying these is that they are going to equal 1, leaving me with just the X. And on the right, at this point too, we're going to go ahead and grab a calculator. What is 246 times 4/3?
328.
Okay, but what did I find? 328 is what? Actually, it's the total pages, yeah. So we want to make sure that we're answering the question that we were asked, which was not what we just found yet, correct? We found the total number of pages. So when you get to the point when you get an answer, just check for yourself, what did I find? Sometimes you're done, sometimes you're not. Here we're not. So I found the total number of pages. So how do I find how many she has left?
Subtracted by how many she's read.
Yep, 328 is how many she has. 246 is what she's already read. And if I subtract that, what do I get?
82.
So there are 82 pages left. Okay, you ready to look at some generous children? Because that's our next problem. Kind and generous children. Al. Al gives 1/2 of his marbles to Jose. Jose gives 1/2 of his marbles to Isabel. Isabel gives 1/2 of her marbles to Letitia. If Letitia was given 4 marbles, how many marbles does Al now have? So in some sense, this problem works really nicely with chapter 1 of this textbook, which is problem solving skills. It actually fits in also through this section because we're doing halves of things along the way. So we're multiplying by 1/2 or dividing by 2 if you prefer. So it's fine. What we're going to do is we're going to write all these characters' names down. You can either write them in the order of they're given in the problem, where they're giving the things away, or in the order that is sort of backwards of that. Either way, like, where do we start? Well, we really are going to start with Letitia because we know how many she has. But I'm going to start with the order they were given. So we have Al first. And then Jose. Isabel. And then Letitia. And we're giving away half. I mean, each of these times they give half of them away. I mean, that's what's happening. It's times 1/2. So that's a geometric kind of a pattern where you're multiplying to get the next term. Or an exponential kind of pattern is what we're actually looking at with this one as well. But we know how many Letitia has. How many does she have? She has 4. So she received all 4 of them from, Isabel. So how many did Isabel have before she gave her 4 away? She had 8. And that was, she has 4 now, if you want to think about it that way. But she had 8. She gave half of them away. But she received hers from Jose. So how many did Jose have?
16.
He had 16. He now has 8, right? But if he received 16, he received them from Al. So how many did Al have?
32.
He had 32, but he has 16 now. So we need to make sure we answer the question that we were posed. What were we asked to find?
How many does Al now have?
How many does Al now have? So how many does he now have? 16. Al now has 16 marbles. Okay, so we're going to stop there.